So this is a dynamics question. We're dealing with forces here, and because the object has to be suspended at rest, the forces have to be balanced. So it's basically a question about making sure all the forces are balanced. You can draw a free body diagram. I'll actually just use the diagram, right, like the diagram that's there. The chocolate ball has a mass and it's going to feel a gravitational force that's not going to be negligible in this case. So there's the force of gravity pointing straight downwards towards the ground. Then it's going to feel an electric force. And the electric force, due to the electric field created by the parallel plates, it's a positively charged metal foil that's wrapping around this chocolate. So since this is a positive charge, it's going to get pushed to the left in the electric field here. Now I'm not sure if I'm drawing these arrows to scale or not. I can do some quick calculations to see if they're to scale or not. Maybe adjust them if I need to. Now, there's one more force actually, and that's the force from the device. This is our fictional field, the chocolate field. That's the device up at the top is creating a field that's attracting chocolate. So it's going to attract this chocolate directly towards it, and that's what's going to balance the forces. I'll call this FC for chocolate force. Yeah, so those three vectors have to balance up and make zero. To get a sense of scale, I'm going to do some calculations here. I'm going to calculate the gravitational force, which will be mg. So the mass is 15 grams, and g is 9.8. So calculator. So this is giving me 0.147 newtons, and that would be aimed down. I'll calculate the electric force. It's in an electric field. Electric force will be Q times E. So the charge placed on this foil that's wrapped around the chocolate is 1 microcoulomb. That would be 1.0 times 10 to the negative 6 coulombs. And the electric field is stated as 8.0 times 10 to the negative 4, or sorry, positive 4. Multiply those together. Actually, 1 times 8 is just 8. And then the powers of 10, negative 6 and negative 4 combine to make a power of negative 2. I'll write this as not in scientific notation to compare it to the gravitational one that I have. So this would be 0.080 newtons, and that would be left. So they're fairly comparable. It looks like the gravitational force is more, but not double. So I'll adjust my arrows a little bit to reflect that. Okay, so the gravitational force is more than the electric force, but not by double. So maybe something like that is a bit better for scale. And how do I draw my diagonal arrow to the right? Well, it has to balance out the other two. So essentially what's going to happen is that I'll actually draw a vertical component that matches the gravity, and I'll draw a horizontal component that matches the electric force to balance it out. And the hypotenuse there, that's going to be my chocolate force. So if I do that, it's all going to balance to zero. I'm going to use some tick marks here. The x components will have to equal, the y components will have to equal. To make it all balance, the x component of the chocolate force, so FCX, the magnitude of it will have to be equal to the magnitude of the electric force, which we calculated as 0.080 newtons. And then the magnitude of the y component of the chocolate force has to balance out gravity, which we calculated as 0.147 newtons. So my overall chocolate force is the hypotenuse here. The magnitude of it is going to be calculated with the Pythagorean theorem. And let me get that into the calculator here. 0.17 when I round to two significant digits. So that's how strong the chocolate force has to be. It doesn't ask for the angle, it just asks for the distance of r. So I don't actually need to calculate the angle. But I do need to calculate r. I need to calculate how far it is. And I know how many newtons I need. If I go back up to the chocolate field description, it's going to be 1 divided by 35 r squared newtons. So basically, 1 divided by 35 r squared has to equal 0.17. I should, since I'm not at my final answer, I should keep a couple of extra digits for now. So I still have it on my calculator, so I'll just write a couple extra digits. And then I'm going to solve for r. So do little cross multiplication type thing. 1 over 35 times 0.1674 will equal to r squared. So r will be the square root of that. I'll just put it all in the calculator now. Okay, so 1 over that value times 35, and I'll square root that. And I get 41 centimeters after all of that. That's how far that chocolate device has to be. So there we go, a make-believe field applied to this dynamics problem of balancing forces.